Hi everyone and welcome to a new video about noise analysis. This is our example number 2 and we continue with resistive circuits. In this example we will look at the different resistive circuits, a little bit different than the first example, and we will also make a comparison between that with this example, and we will see what the actual difference is between the two circuits. So again, we will look at calculations and also simulations in SPICE to verify our calculations. So this is the circuit we have given in this example. As you can see here, the resistor values are 1 mega ohms and 3 mega ohms. These are actually 1000 times larger than the example number 1. So in this example we have 1000 times larger resistors, but you also see that the circuit is exact same as in previous example number 1. What we want, again, we have several calculations. We want the output noise, voltage, spectral density. We want the input noise, voltage, spectral density. We would like to have a total RMS, output noise, voltage, of course at some specific signal bandwidth, which are given here, as we did in the previous example. And we would like to have the signal to noise ratio SNR. So let's look at the solutions. Before we move on, we will of course use a procedure. Also in this case, we will disable all independent sources in this case. So this is actually one of the independent sources we have here. This is the VIN. That will be a short, and if this is a current, so that will be an open circuit. Now we will use, in this case as a model, noise voltage sources associated with each resistor. So for each resistor we will have a noise voltage source in series with a noiseless resistor. So the model will then have these two noise spectral densities in the model, which is actually shown here. So this resistor R1 will then be replaced by a series combination of the resistor, which is now noiseless, and the noise voltage spectral density of that resistor. In the same case for the R2 also, we have the R2 now in this case, which is the real resistor. This is now the noiseless resistor with its own noise voltage spectral density. So that's actually what we have, and as you can see, the input voltage source is shorted. And we will use superposition principle to calculate the required values here for the calculations. As a recap again, the terminal noise power spectral density is given in general form as this expression, which you can see here, the noise power, which is the noise voltage squared, noise voltage density squared, which is then 4kTR. And this will be clarified shortly. We have already done this, of course, in example number 1, but I will go through this also again. We also have the noise voltage spectral density, which is then just the square of this value. So which is just, if you take the square root of that noise power spectral density, you will get this result. And you can see that the units are also correct. So what is the K? K is a Boltzmann constant, just a constant, and this is the value of 1.38 times 10 to the power minus 23 joules per Kelvin approximately. You can of course have a little bit more accurate value if you look at the table. The T is the absolute temperature given in Kelvin, so not on the degrees. And for room temperature operation, what we most of the time assume in these examples, we have 27 degrees, but that is in Kelvin, 300 Kelvin. The R in this expression for this formula is the equivalent resistance which you see at a node. For example, at this node you will see some resistance that will not be used in this formula. That's what we have actually as a general introduction, and we will now use these values and also these formulas to determine the required values in the calculations. So let's move on to the next step. The noise voltage spectral densities for each resistor. That is what we will use, and this is the model we will then use for that one. For R1 we have this formula, of course, and then specifically the R1, and now this is then 10 to the power 6 ohms, which is then 1 mega ohms. Now if you do the math here, just substitute the value for the K and also for the temperature, of course in kelvins, then you will have this value, 128.7 nanovolts per root hertz. Now if you do the similar form for R2, just substitute value for the R2, in this case 3 times larger, 3 mega ohms, then you will have 222.9 nanovolts per root hertz. That's what we have, and then using superposition, we will of course use these noise spectral density sources and the resistor values to determine the output contribution at the noise. So what we have is then the output noise spectral density due to only this source, which is then of course assumed that to be active and the rest of the sources are shorted or inactive in this case. Then we have this expression, just voltage divider rule, you know this, and then if you do the math here you will get 96.54 nanovolts per root hertz. Now, if you do similar form for R2, you will have this. Of course, if you look at R2 and the source for the R2, which is then the E sub n R2, then you will of course disable this one. And if you look at this node, then this is actually the resistor where you take the noise voltage, and then they have this expression. And if you now do the math again substitute the required values, you will have the following 55.74 nanovolts per root hertz. Now we have now the required contribution at the output for each noise voltage spectral density. And now if I now of course want to combine these, because I want to have the total effect, because these are the partial effects. We have the partial effect of the R1 and the partial effect of the R2, of course with its own associated sources. Then we have the following expression, which is then the output, total output noise voltage spectral density, which is given by E sub n, comma out, which is then the total output noise spectral density, which will then the square root of the square of this value plus the square of this value, which is then the separate contributions, and then sum them up, and then in the square root, and you will have then this expression, which will be then 111.5 nanovolts per root hertz. That's what we have, and we will use this of course for further analysis. We already know now one of the unknowns in our calculation, because we had 4 calculations to be done in this exercise. One of them was the output noise voltage spectral density, and this is already seen here. So let's then look at an alternative calculation, because this is not only way to do the calculation. You can also use, instead of the series combination of the noise resistor and the noise voltage spectral density, you can also make this R1 in parallel with the current source, which is then what we call the Norton equivalent. So this is what we have in this model, which is called the thevenin equivalent circuit or thevenin model, but this is now also can be done in Norton equivalent model. And then we have a different noise circuit. The required parameters are then the equivalent resistor are equivalent, and we have the total input current noise actually for this circuit. That is actually what we really require. So we need to determine these two parameters. Now for this circuit, when you look at the output and you disable actually all the sources, just looking at the resistor values, then you will have the R1 and R2 in parallel, which is straightforward, because if you short this and short this, you look at this node between these two nodes actually, then you will see R1 and R2 in parallel. And if you do the math here for the parallel combination of two resistors, you will get 750 kilo ohms. We had 750 ohms in example number 1, so you can see that this is actually 1000 times larger than the example number 1. Okay, now noise current spectral density due to R1 is then given by this expression. Again, this is the transformation from the thevenin equivalent circuit to the Norton equivalent circuit. So what we do is we take this source, which is then the noise voltage source spectral density, you divide it actually by this resistor, and you will have your noise current spectral density. That's actually what we've done here. So that is actually just using Ohm's law to transform the thevenin equivalent circuit to the Norton equivalent circuit. Then you will have this value, which is 128.7 femtoamps per root hertz, which is very small actually in the current. If you do a similar form for R2, just divide by this source divided by the R2, you will have this value. Now, if you now combine these two separate noise current spectral densities, you will have the total input noise current density, and which is then given by this expression. Just do the math for yourself. It is exactly the same procedure as we did also for the output noise spectral density. Then you'll have this value. Now, this is of course the noise current which you have now here. And if I now want to calculate what is on the output noise voltage spectral density, you will just use Ohm's law. Ohm's law says current times resistor. We already have the resistor. We will now have also the current noise, which is then in this case the input current noise, which is also of course the output current noise, because it's just in this case exactly the same. Then we have this output noise voltage spectral density. Just substitute the values for the input current noise density and also the resistor, which is 750 kilo ohms. You will get 111.5 nanovolts per root hertz. And this is exactly the same result using the superposition principle. So it doesn't matter how you do it, which you of course preferred, but it's the exact same result. So let's then move on with the next step, which is then input noise voltage spectral density, which is given by small letter E sub n in. We will for that use the signal gain, because we already know that we already know the output noise spectral density, so we can use the signal gain, actually the noise gain, to calculate then what the value of the input noise voltage spectral density must be. Now the signal gain is of course the input node to the output node transfer, and for that we can use the voltage divider rule in this circuit, which is then the gain, signal gain, is R2 over R1 plus R2, just the voltage divider rule. You will have 3 over 4. Again, I must emphasize also here, specifically, if you want to be very accurate, you really need to use the noise gain. But in this case, the noise gain and also the signal gain are exactly equal to each other, but it doesn't have to be equal to each other. For example, in op-amp circuits or transistor circuits, you will see that this is not the case. Okay, now using the signal gain and also the output noise spectral density, we already calculated this, we can calculate the input noise spectral density, which is again using this model, noise model. We know that the output noise spectral density, noise voltage spectral density, will be then the gain times the input noise voltage spectral density. Now if you rewrite this, you will have then the input noise voltage spectral density, which is then the output noise spectral density divided by the signal gain. But in this case, the signal gain and the noise gain are exactly the same, but this must be of course in specific form the noise gain. Now if you do the math, you will get this, which is then what we had already, 111.5 nanovolts per root hertz divided by the 3 over 4, 0.75, you will get this. So this is the value what we have for our input noise voltage spectral density. Now the next one is the total RMS output noise voltage. This is really important, and for that we integrate the output noise voltage spectral density across the complete bandwidth, and in this case the complete noise bandwidth. So you have the signal bandwidth, but also noise bandwidth. Again, this is a passive circuit which is not frequency dependent, so there's no cutoff frequency, there is no any other frequency limiting part in the circuit. So the signal bandwidth is infinite, but the noise bandwidth is then also infinite. And noise bandwidth is then also equal to the signal bandwidth, because there is no dynamics in this circuit, so it is a zeroed order circuit. That's actually what we have here, a very special case. Okay, then the following formula can be used to go from the spectral density to the RMS value of the noise, which is then the spectral density for the output noise times the square root of that noise bandwidth. And then we have the RMS noise value. So if I now look at several frequencies, so the total RMS output noise voltage for several frequencies, let's start with the noise bandwidth of 1 kilohertz, which is one of the frequencies we have given in the calculations. Then we have this, and this is just the value for the output noise voltage spectral density, which is of course always the same, but this is another frequency which you use and you will get this value. Now if you now have the 10 kilohertz, which is 10 times larger, you will have this, just this changes, and then you have this value for your RMS output noise voltage. Now if you go also for the 100 kilohertz and also for the rest, you see that this pattern will be created. And you can see that this RMS voltage are also increasing. For example, if you look at 1 kilohertz and also to 100 kilohertz, which is then an increase of 100 times in the frequency, then the RMS output noise voltage will be 10 times larger. So 100 times increase in the frequency will increase the RMS output noise voltage by factor of 10. Of course, this can be shown in a more nice way in a table. This is the frequency band where we're talking about 1 kilohertz up to 1 gigahertz. And this is the total RMS output noise voltage. You can see that this is then the table. And you can see again 1 kilohertz, 100 kilohertz, 1 megahertz, for example, for several frequencies, that indeed the output RMS noise voltage will increase according to this formula. So let's look at the next step, which is the signal to noise ratio, SNR. And again, as a reminder, signal to noise ratio, SNR, is a measure that compares the desired signal level to the noise level. We don't want that noise level, but there is of course some noise. And we are of course interested in the desired signal level. We would like to know what the ratio actually is, so we would like to compare that, and that value is then given by the signal to noise ratio. So the signal to noise ratio is a ratio defined as the signal power to noise power, and often that is expressed in the units dB. A ratio larger than 1 or higher than 1, it means actually greater than 0 dB. That means you have more signal than noise. And of course in dBs, if you have a larger value than 0 dB, that means actually you have more signal to noise. If you have a smaller value, for example minus 20 dB, then you have more noise than signal. And that is actually definitely not what we want. Now for this circuit, the SNR at the output for a specific frequency can be calculated using this formula, which is then 20 log, already given in the dBs, 1 over that output RMS noise voltage. Now this is what we had calculated for our total RMS output noise voltage for specific frequencies. Then we can use this with the signal bandwidth or the noise bandwidth and then calculate the SNR for the signal to noise ratio at the output using the formula we have given here. So if I now look at 1 kilohertz and then substitute what we have here, I will have 109 dB. And if I move on, I will have then for the 10 kilohertz, I will have 99 dB. If I move on, it will be 89 dB, 79 dB, 69 dB, 59 dB, and I have 49 dB for the 1 gigahertz. What you see is actually if I increase the frequency by a factor of 10, again 10 times, 10 times, 10 times, 10 times, 10 times, you will see that this will decrease by 10 dB. So there is actually some relation between the frequency and also the SNR. Of course, decreasing your SNR means that your signal to noise ratio will decrease, so your noise level is coming closer to your desired signal level. So if I now combine these these values here in a table, and again show this also in a table to emphasize where we get this value for the SNR, then you get with 1 kilohertz, you can see that this is 109 dB. And if I increase this, for example, to 1000 times the frequency band, noise band, which is then 1 megahertz, you will have then a decrease of 30 dB, which is then of course 3 times 10 dB decrease. That's what we have now for SNR. That's the calculation. So conclusion now here, the larger the frequency band, the larger the noise bandwidth. I mean noise voltage. So if you increase your noise bandwidth, your frequency, your operating frequency, that's of course in some cases nice, because then you have a really high speed response. That's of course really nice. You have your rise time, which is very short, but you can have a larger noise voltage and also smaller SNR. This is of course a consequence of a larger noise voltage. And that's what we have here. So let's also look at the simulation results. First, output noise voltage spectral density. This is what we have. You can see this line is the output noise voltage spectral density. You can see that this is 111.5 nanovolts per root hertz. And we had calculated also that one. using, of course, a Norton equivalent circuit, using that equivalent resistance and also that input noise current spectral density. And then you can see that it's exactly the same. And this is for this circuit. So this is actually a confirmation also in the simulation. If I now go to the input noise voltage spectral density, you can see that it's also frequency independent. It all stays the same, the density. And you can see that this is then the value. And if I now look at my calculations, it was 148.6 nanovolts per root hertz, and I see here 148.7 nanovolts per root hertz. It's approximately the same, so I'm rounding off errors, but this is nice confirmation also in the simulation. So the input noise voltage spectral density is also confirmed in the simulations. Now let's also look at the total RMS output noise voltage. This is the plot. You can see at several frequencies I placed the labels, so these are the labels. You can see it is actually increasing rapidly at some point, and this is of course also given in the log scale, so that is of course 10 times, 10 times, 10 times, 10 times increase. But if you go, for example, from 1 kilohertz to 10 kilohertz, the increase is not that much. But if you go from 10 kilohertz to, for example, 100 kilohertz, the increase is actually much larger. That's actually due to that action. But if you combine these, all of them, and using this formula, and of course also using the output noise spectral density value which we have calculated, then you have this table. You can see that this is then the value for your frequency. If you of course go again from 1 kilohertz to 10 kilohertz, and then from 10 kilohertz to 100 kilohertz, this is of course 10 times larger, but difference is here 9 kilohertz. And if you go from 10 kilohertz to 100 kilohertz, then the difference is then 90 kilohertz. So it is of course 10 times larger, but there's a 90 kilohertz difference. So that's why we have also a larger difference in the noise voltage. You can also see the values here in the table. And this is also a confirmation. Look at this value. For example, at 1 kilohertz, you can see that it's very close to what we have here. So this is 3.525 microvolts, but this is 3.526. It's very close to actually what we have. And if you compare to the rest, it's also very close to what we have here, or most of the time also exact the same. So this is what we have now. Let's also look at the signal to noise ratio, which is the SNR for this. You can see the plot here. It will decrease. It's sort of very high. It's some very low frequency, 1 millihertz, and then if you move up with the frequency, you can see that the signal to noise ratio will decrease. And you can also see, using this formula, of course, that this table is in confirmation with the values here. So if you look at this SNR at 1 kilohertz, you can see that is 109.1 dBs, which is 109 dB here in our calculation. So that is a nice result. And also for 10 kilohertz, you can see 99.1 dB. That's also in agreement with our value at 10 kilohertz. And if you look, for example, at 1 gigahertz, it is 49 dBs. It is here 49.1 dBs. So that is again in confirmation what we had in our calculations. This is the calculations, and this is just a simulation result using this circuit in our SPICE simulation. As I already said, we can compare this with our example number 1, where we had the values of R1 and R2 as 1 kilo ohm and 3 kilo ohm. So this is of course 1000 times larger, but let's also look at what the effect is of that to our noise performance in our circuit. So let's make a comparison. The first comparison, using these two circuits, you can see that R1 and R2 for 1 kilo ohm and 3 kilo ohm for Vout1, and 1 mega ohm and 3 mega ohms for these two resistors for the Vout2. So this is the circuit we have in this exercise, in this example. But the previous example, example number 1, had these two resistors. Now, if I made this simulation using these two circuits, these two voltage dividers, and I made a plot of that output noise spectral density, which is actually shown here. You can see that the value here is 111.5 nanovolts per root hertz, and this is then 3.52 nanovolts per root hertz. You can see that there is a large difference between these two, even though that the signal gain is 3/4, 0.75, That might be, of course, interesting for some applications, but your noise is, in this case, the output noise voltage spectral density is much larger. So that is also something you really need to consider. That also counts for the input noise voltage spectral density. This is, of course, the input noise spectral density. So you can see that this is then much larger compared to the input noise spectral density. Again, this is an input noise. It's actually some error here. Okay, now let's also compare the total RMS output noise voltage for the situation where you have the 1 mega ohm and a 3 mega ohm in this case, and also compare that to the 1 kilo ohms and 3 kilo ohms. You can see that this is much larger in this two resistors where we have 1 mega ohm and 3 mega ohms. Again, the total RMS noise voltage is much larger for two resistors, which are much larger than in the first example. You can also see that from the SNR in different form. If you have a R1 as 1 kilo ohm and R2 is 3 kilo ohm, and then you have an R1 of 1 mega ohm and an R2 is 3 mega ohm, so 1000 times larger, you can see that your SNR is also decreasing. In this case, your SNR has decreased actually by 30 dB, just looking at the resistors. So decrease of your increase in your resistor by 1000, by a factor of 1000, you will decrease your SNR also by a factor of 1000. I mean by a factor of 1000. That will be then, in this case, of course, a decrease of 30 dB. So that's actually the signal noise ratio, the performance. This is of course all linked to the RMS output noise voltage, also to the output noise voltage spectral density. This is the input noise spectral density. So it's all linked together, but you can see that in the signal to noise ratio in a little bit different form. And again, if you want your signal gain just 3/4, you can of course use 1 mega ohm and 3 mega ohm instead of 1 kilo ohm or 3 kilo ohm, but you will have much more noise, and that is something you really need to consider. Of course, if you say I want to make it 1 ohm and 3 ohm, because that's of course maybe a solution to make the noise even lower, but then you will have of course more power consumption. So there is actually some optimum. So you really need to take several aspects into consideration. Now we have seen this now in the simulation, also in the calculations. We have verified our calculations in the simulations and also compared the example number 1 and example number 2. I will now move to the actual simulation in the SPICE, and I will see what will happen there, and you'll see how I generate these plots. So let's jump to the SPICE. So this is the SPICE simulator. I have already set up the circuit with R1 and R2, 1 mega ohm and 3 mega ohm for the R1 and R2, and this is the voltage source. Again, if I click on it, it doesn't really matter what you choose for your signal. It can be a step, it can be a sine, it can be a square root, a triangle, it doesn't matter. Just an AC source. It must be an AC source. You cannot use it as a DC source. That won't generate the required noise plots. You go to the analysis. In this case, I use Tina TI SPICE. You go to the analysis, then you do noise analysis, and then you choose your frequency range. I start at 1 millihertz and I go all the way to 1 gigahertz, and this is the number of points to make the accurate plot. So I have found out that this is actually the best you can make in this simulator, and these are the diagrams I can choose. You can of course select different plots. I want to have of course all of them to check what we had. So the output noise, input noise. So the output noise means actually output noise voltage spectral density. Input noise means actually input noise spectral density. Total noise means total output RMS noise, and the signal to noise ratio is of course what we have done in a final calculation. So let's run this. I can just click OK, and then we will generate the plot, and I will make it larger. Okay, this is the output, and this is the frequency range. Let me make the frequency range a little bit easier to see, and also the size of the font setting. Okay, and also here, so I will just start at 0, you can see that, let me make this also 120 nanos. You can see that this is the value of our noise, output noise voltage spectral density at some frequency, but if I change the frequency, it doesn't really matter. It stays the same. And that's actually what we have, of course, also have seen in the calculation, also the discussion of the simulation results. That is for the output noise spectral density. I will now move to the input noise spectral density, which is then this one. So again, I will make the font 18, and I will now change it from 0 to, let's say, 116 nano, so you can see the line much clearer here. And I will also make this 13 steps, and then going from the font size 18. Okay, now you can see that also much clearer. Let me make this also blue, just to give you a better view of this one. And if I now look at the label, you can see it's 148.66 nano, and I had 148.7 nanovolts. And for specific frequency, you can see that here. But if I go on, and if I go all the way to 1 gigahertz, 1000 megahertz, it still stays the same. It doesn't really matter. So I can also use a different label. You can see that the change is 0. It's all the same. Now I will now go to the output noise as this. You can see the plot here, and I can of course change the label here with this. Okay, that's fine. And I can also make this 13 times. I had 13 ticks, and of course the font settings a little bit easier to see for you, and also make this blue. It's a bit clear. You can see indeed that this is increasing if the frequency is increasing. So that is of course also the confirmation. Let's also check that just for, let's say, 1 gigahertz. You can see it 3.53 millivolts RMS, of course. And if I go to, for example, the 1 kilo and also the 1 giga for two different values, you will have this one. Of course, if I look at 1 mega, I have this. So you can see these are also what we had in our calculations. So again, a confirmation of what we have in our calculations. I will now move to the signal to noise ratio. This is what we have here, signal noise ratio. So if I now look at the table, I'm in the graph, you can see that this is decreasing. At some point it will stay at a linear decrease at a log scale. And if I look at, for example, at 1 kilohertz, just type in 1 kilo and then to enter, you will see it is 109.05 dBs, which is what we had. We had 109 dBs. So this is actually in agreement with our calculations. And if I now move to 10 times larger frequency, 10 kilohertz, you will see that this is indeed a change of 10 dBs in Y direction. If I change the frequency from 1 to 10 kilohertz, which is 10 times, but the difference is of course 9 kilohertz. If I now go to, for example, 10 and then 100 and then do this, I also want to have it different. This is then again a decrease in the signal to noise ratio of 10 dBs, but this is of course a change of 90 kilohertz, but the increase in the frequency is again 1 decade, which is just 10 times. So this is actually also again a confirmation of our calculation for the signal to noise ratio. So that's for example number 2. We have seen the calculations for actually the same setup for the voltage divider circuit, 2 resistors that create actually a voltage divider, but the resistor values are 1000 times larger, and we have seen what the effect of that was for our noise performance. In the next example, we'll also look at frequency selective circuits like an RC circuit, and we will see what happens with our output and also the input noise voltage and also the SNR. So I will see you next time, and if you have any questions about this, please let me know. I will try to answer them as soon as possible. Thanks again, and see you next time, and don't forget to like and share so that we reach more people. Thanks for your cooperation, and see you next time.